So maybe I can use this time to introduce you here, Julio. First of all, thank you so much for being here with us um, and talking to us about supporting production science at major facilities by leveraging research and educational networks. Julio has been working in this area for quite a while. He's a research professor in the Knight Foundation School of Computer Science in the College of Engineering Computing and the Assistant Vice President for Technology Augmented Research in the Division of IT at Florida International University. He's responsible for furthering the mission of the Center for Internet Augmented Research and Assessment, CHIARA, to contribute to the pace and quality of research at FIU through the application of advanced cyber infrastructure. And I know, Julio, you've been working on data flowing from the major facilities from across South America to the US and other locations as well. So we're very pleased to have you today, and I'll give you the floor.
Thank you, Eva. And I'd like to thank also the CI Compass team for the opportunity to present to you today. As Eva mentioned, my name is Julio Ibarra, and I'm based here at Florida International University. And the title of my talk is Supporting Production Science at Major Facilities by Leveraging Research and Education Networks. Okay, so let me start off with some context and the motivation behind this webinar. So I attended the NSF Research Infrastructure Workshops in 2023 and 2024. I also participated in the Cyber Infrastructure for Major Facilities 2024 Collaboration in Action Workshop. And major facilities were the focus of much discussion at these workshops. Some observations I made about the major facilities and their challenges are the following. Designing, building, and operating cyber infrastructure for major facilities is increasingly challenging. Changes that happen during the life cycle of the project, for example, during planning and design, construction, operations may require periodic enhancements. Decisions that were made at design time may need to be changed when the major facility enters implementation and operational phases. Data archival is an increasingly important issue. Storage needs for major facilities is increasing. Preservation of scientific data for future generations is critical. Major facilities must make cost assessments. For example, what proportion of total cost should be allocated to data archiving? So there's a lot of discussion about how clouds, or there were a lot of discussions about how clouds may be a solution for operations and data archival for the major facilities. Challenges to transitioning to the cloud is the CI Compass community has done an outstanding job in documenting this. They have a working group on the cloud, and I cite here one of the reports that I went through in preparing for this workshop. But at the 2023 Research Infrastructure Workshop, the CI for Major Facilities 2024 and the Research Infrastructure 2024 workshops, these challenges were reported on the efforts to transition to the cloud. For example, managing costs was reported as one of the biggest challenges for major facilities. Costs are incurred for data storage, egress, compute resources, serverless functions, data movement, API requests, and many other types of services. Vendor lock-in is a big problem. Transitioning between cloud vendors can become very costly because of differing APIs, tools, and differing services. CI design for the cloud and/or on-prem is challenging. The report suggests that an all or nothing option is most likely not best for a workable solution. Also, workforce training is an essential investment as well to be able to effectively use the cloud. So after attending these workshops, I was left with the following question, and Eva might remember the conversation we had. You know, why are the major facilities and the NSF paying for cloud services when the CI ecosystem contains a plethora of infrastructure resources with experienced and talented people that can be leveraged? So in other words, these resources, since they're leveraged, they're already funded. And I was left with this question about, well, why are we not taking advantage of these resources and capabilities? So I posed the following question, or I posed the following claim to all of you. The national CI ecosystem offers a plethora of options for major facilities to achieve their goals by collaboratively building effective solutions to serve the goals of their mission. So I want to be clear that, you know, I have nothing against clouds, and I agree with the CI Compass report cited, where they quoted, while the cloud introduces a myriad of complexities, its advantages are manifold. However, if solutions can be built by leveraging the R&E networks and the resources of the CI ecosystem, then why invest in a cloud solution? So that's my thesis here, and so I want to pose the following question to the CI Compass community. How can major facilities leverage R&E networks to build effective solutions to serve the goals of their mission? So to answer this question, I will present the following topics: a brief review of the fundamentals of research and education networks to define some terminology and some fundamental concepts, a sampling of the R&E network ecosystem that can be leveraged by the major facilities, measurement and instrumentation and resources of R&E networks for monitoring, measuring, tuning, and troubleshooting CI resources, major facilities leveraging R&E networks, some examples of major facilities collaborating and leveraging with R&E networks, and also an SLA-driven science use case, the Vera Rubin Observatory. Propositions after each section, I will include them to summarize key points and to stimulate discussion in the Q&A. I will then conclude, and I will try to cover these topics broadly, so to leave enough time for questions. I will try to avoid going too deeply into them. So let's start with the fundamentals of R&E networks. So R&E networks are sponsored and operated by R&E organizations. You have universities, for example, FIU, USC, regional networks that cover, let's say, a state, such as Florida. You have Florida Lambda Rail or Scenic in California. And you have national research and education networks, such as Internet2 and ESNet. I also will refer to the NSF International Research Network Connections, IRNC program, that provides international connections to research and education networks in other countries. So R&E networks span a territory or a region to serve their community of practice. So for example, Florida Lambda Rail serves the R&E community of Florida, Scenic of California. R&E networks are mission-oriented, typically sponsored by a government or a community of practice. NORLab, for example, operates a production R&E network to support 5 programs. CTIO, which is the Cerro Tololo Inter-American Observatory, CSDC, which is the Community Science and Data Center, the Gemini International Observatory, KPNO, which is the Kitt Peak National Observatory, and the Vera Rubin Observatory. Another example is the ESNet network, which is a high-performance, unclassified network built to support science research, providing advanced networking services to more than 50 DOE research sites. More on the fundamentals of RNE networks. So RNE networks conduct experimental research to support continued technical evolution of the RNE network. So many of the awards out of the Office of Advanced Cyber Infrastructure leverage RNE networks to deploy novel technologies such as software-defined networking, programmable data planes, in-band network telemetry, in-network computation. Some examples are the AMLITE project. You also have the Fabric network, which is a national testbed network, and you have ESNet. Collaboration and cooperation are core tenets of RNE networks to support research and education and the mission of their stakeholders. The Vera Rubin Observatory Long-Haul Network is an example. It's built from a collaboration and cooperation of 10 RNE networks. For Vera Rubin, we leveraged interconnected RNE networks to build diversity and resiliency. Another example is contributing available bandwidth to support projects. The National Research Platform nodes are hosted at regional networks and the Internet 2 network. So for some of the information I have here in this section of fundamentals of RNE networks, I found an interesting RFC written by Vince Cerf that has a lot of these concepts documented in there, and also the NSF IRNC program announcement is also a very good read for some of these concepts for understanding RNE networks. So moving on to a sampling of the RNE network ecosystem. I'll present a small sample of the networks in the RNE ecosystem. Unfortunately, there's not enough time to cover all of them. So I'll start with Internet 2 and the regional networks that connect to Internet 2 through the Quilt. Internet 2 and the regional networks connect the RNE universities and institutions in the US. In addition, they connect many other networks and projects funded by the NSF. You can see how interconnected all of these states and parts of the US are through these many networks that participate in the Quilt and also Internet 2. The ESNet 6 National Research and Education Network is the current generation of the ESNet network. It connects the Office of Science, National Labs, the National Nuclear Security Administration, and NSA labs, and other DOE labs. In addition, ESNet supports projects to conduct research, such as the NSF Fabric project. Also, you could see here on the right side here how the ESNet network extends into Europe to support the high energy physics community. In this section, I'll present some projects and collaborations to connect the RNE communities in the US to other countries where major facilities are located. Collaboration is a key underpinning of the success of these projects. I'll start with the Advanced North Atlantic ANA collaboration. It's a collaboration that connects the US to Europe across the North Atlantic. The members that participate in this collaboration are Internet 2, Canary, the NREN of Canada, ESNet, GÉANT, the regional network of Europe, NordUNet, the regional network of the Nordic countries, SURFnet, the NREN of the Netherlands, the NEAR project at Indiana University. In aggregate, all of these network segments you see across the North Atlantic aggregate to 2.4 terabits of bandwidth capacity. Make note of just how much bandwidth we're talking about here, available for use by the major facilities. The Pacific Islands RNE Networking PIRIN project is an IRNC award to the University of Hawaii. David Lassner is the principal investigator. So PIRIN connects US territories in the Pacific to Hawaii and the mainland US. The encircled islands, as you see here in the map, let me see here. So, are connected through PIRIN. PIRIN has extensive collaborations also with the international and national R&E networks of the Pacific Rim countries. You could see how extensive the network fabric is from an island like Guam, which has an exchange point that connects many networks in the Pacific and in Asia to the US. The Pacific Wave International Peering Exchange, it operates a peering exchange fabric that spans the west coast of the US and extends to Chicago. R&E networks of Pacific Rim countries connect to Pacific Wave to connect their R&E communities to the US and to other countries. This is a very extensive network here. You could see here many of these networks come from other countries and also the connections to Tokyo and Guam. It's a very rich fabric of connectivity along the Pacific. One of my favorites is the AmLite International R&E Network. It's a project based at FIU, and I am the principal investigator of the project. And this project specifically extends the R&E community in the US to Latin America and also West Africa. We have up to 600 gigabits of upstream capacity between the US, Latin America, the Caribbean, and 100 gigabits to Africa. Our plans are to increase the capacity to 1.1 terabits per second between Florida and Brazil, either late this year or early next year. Hopefully, we'll have this in place in time for supercomputing. We operate exchange points, 3 in Florida, 1 in Atlanta, Georgia, 2 in Brazil, Chile, Argentina, Puerto Rico, Panama, and South Africa. And these are important resources for the interconnection of R&E networks. We operate a production software-defined infrastructure. It's been operating since 2014. The network has a number of rich capabilities, such as deeply programmable devices, such as the P4 data plane. We also collect telemetry. This is fine-grained telemetry to be able to do real-time measurement. We also can support runtime network verification through policy-driven networking so that when events occur, we can have the network reprogram itself to respond to those policies, and closed loop orchestration for automation and autonomic control operations. The network is highly instrumented to support troubleshooting, monitoring, measurement at a very fine-grained level. And one more project I want to mention out of the IRNC portfolio is the Network Startup Resource Center. This is an engagement project that supports a participation of under-resourced countries to participate in the global R&E fabric. And this group at the University of Oregon with Stephen Hooter as the principal investigator has been doing extensive work since 1992 to be able to have these under-resourced countries be able to participate in R&E networking, which is very relevant for major facilities because in some of these countries, there are instruments and facilities that operate and would benefit from the use of the R&E networks. And you can see in this map here the extent of their work since the 1990s to 2023, how many different sites they have visited and collaborated with people by providing workshops, assistance with infrastructure, technical conferences, and tutorials and presentations. So to wrap up this section, I want to provide some propositions about what we've covered. So R&E networks have an abundance of bandwidth capacity. If you recall, with the ANA, the Advanced North Atlantic collaboration, as well as the AmLite project, and many of the network segments you saw in the Pacific, there is an abundance of bandwidth capacity available for major facilities to be able to use these networks. The R&E networks span local, regional, national and international geographies to support their communities of practice. R&E networks are well connected, forming a global fabric of network connectivity, and major facilities in remote locations can leverage the R&E global fabric of network connectivity to accomplish their science. So I want to move on now to the monitoring, measurement, instrumentation, and resources section of the to discuss some of the monitoring and measurement, instrumentation, and tools and resources that can be leveraged on the R&E networks that could be very valuable for the major facilities. The greatest value is in the expertise of the network engineers and specialists in the R&E networking community using these tools. So I want to start off with the some network performance and troubleshooting. We have Sonar, which is a tool for end-to-end monitoring and troubleshooting network performance. It's been widely adopted by the R&E community, and it's used extensively for network troubleshooting. And the Engagement and Performance Operations Center. This is a team that provides researchers with a holistic set of tools and services needed to debug performance issues and enable reliable and robust data transfers. The EPIC team supports, or EPIC project supports, 5 main activities: roadside assistance and consultation, application deep dive, network analysis, data mobility exhibition, coordinated training. As an example, the IRNC projects and the EPIC team are working together with the Event Horizon Telescope observatory sites to transition their data movement from site to correlator using R&E networks instead of how they traditionally move their data, which is by shipping disks. This provides you with an example of a Sonar network that has been built for the Vera Rubin Observatory. The green hexagons that you see here represent Sonar instruments deployed throughout the network to span all the way from northern Chile to the USDF facility at SLAC in Menlo Park, California. For some other tools and resources, there's the network performance resources for major facilities. ESNet has developed a knowledge base for engineers and for scientists to be able to do tuning of networks, of data transfer nodes, and also for using these tools for data transfers and also for deployment of a science DMZ at campuses or major facilities. This is an extensive knowledge base that our engineers use extensively when working with researchers. To end this section, a few more propositions. So R&E networks have very experienced and talented network architects and engineers to design and build networks for major facilities. R&E networks have a comprehensive set of tools and resources for monitoring, measuring, tuning, and troubleshooting networks to assist major facilities achieve their goals. So let's move on in this section here, and I will present a couple of examples of major facilities that are leveraging R&E networks. So the first one I would like to present is NORLAB. NORLAB is the National Optical Infrared Astronomy Research Laboratory in the US. It's a US National Center for Ground-Based Nighttime Optical Astronomy. NORLAB leverages many R&E networks in the US, Canada, South America, and South Korea. For example, CTIO, the Cerro Tololo Inter-American Observatory, is a complex of astronomical telescopes and instruments located in northern Chile. At an altitude of 7,200 feet, CTI hosts a total of 40 telescopes for mapping and doing observations to the southern hemisphere of the mapping the southern hemisphere. The Gemini Observatory consists of twin 8.1 meter diameter telescopes located in Mauna Kea, Hawaii, and Cerro Pachon in Chile. The Kitt Peak National Observatory is located in Tucson, Arizona, at an altitude of 7,000 feet. It hosts facilities that operate more than a dozen optical telescopes and 2 radio telescopes. Give me a second. And the Vera Rubin Observatory is currently under construction on Cerro Pachon in Chile. It is an 8.4 meter telescope. It's coupled with a 3,200 megapixel camera. It's the world's largest digital camera ever fabricated for optical astronomy. So here's an example of or representation of the NORLab network that connects all of these different sites and supports networking services for these observatory sites. And the NORLab network connects to the research and education networks supported through the NREN of Chile and the regional network of Latin America, as well as the AmLight network. Another community that leverages research and education networks is the Large Hadron Collider community for high energy physics. LHC1 is a private network that connects the tier 1s and tier 2 sites. It's all about sharing network resources. It's a collaboration among 30 national and international R&E networks, and it consists of 110 connected sites. And the NSF Campus Cyber Infrastructure Program. I included the CC STAR program in this section because I think it's important to recognize how much cyber infrastructure can be leveraged at the campus level. CC STAR funds networking, compute, and storage at the campus level. It provides support for science DMZs, requires a minimum of 20% resource sharing for compute and storage awards, and the awards can leverage path or access for resource sharing. The number of compute and storage awards on campuses is significant and growing. You could see here in the legend the number of awards that have been made for compute only, storage only, and compute and storage both. The program has made over 500 awards. These resources can be leveraged by the major facilities through PATH and the Open Science Grid. Major facilities at campuses are leveraging the shared cyber infrastructure from the CC STAR program. So for example, NORLab at the University of Arizona is doing that, and so is NRAO at the University of Virginia in Charlottesville. Okay, so propositions to finish this section. The major facilities are leveraging R&E networks and resource providers to achieve their goals. Collaborations between major facilities, the R&E networks at the campus, regional, national, and international levels, and the resource providers, by leveraging shared CI, can provide cost-effective solutions. In this section, I will present the Vera Rubin Observatory use case and the R&E network that was built in response to the SLA that Vera Rubin has. So here's a description of the Vera Rubin use case and its SLA. So Vera Rubin is a large aperture, wide field, ground-based optical telescope that's under construction in northern Chile. The telescope will take a picture of the southern sky every 27 seconds, referred to as the transfer window, and it will produce a 13 gigabyte data set. Each data set must be transferred to the US data facility at SLAC in Menlo Park, California, within 5 seconds inside the 27-second transfer window. Challenges that the network will face in being able to respond to this SLA in use case is high propagation delay in the end-to-end path. The round trip time from the base station to the base station in northern Chile to the USDF in Menlo Park, California, is approximately 180 plus milliseconds. 0.001% of packet loss will compromise the Rubin Observatory application. These are some very rigid constraints in which the network was built. The map that you see here on the right represents the topology for the Vera Rubin long-haul network. The segments in green represent the primary path for the data movement. The segments in white represent the backup paths. So this is a very detailed diagram of the Vera Rubin Observatory long-haul network. So we refer to this as the LHN. The LHN was designed and built to respond to the Vera Rubin SLA. There are 10 research and education networks collaboratively and cooperatively that worked together to build and operate the LHN. The LHN leverages the RNE network infrastructure of these RNE networks, and operations is scheduled to start in July 2025. So this network has been built to deliver every image from the telescope to the USDF, and it shows just how complex it is, but it's already built and it's being tested with many different test scenarios to make sure that it will meet the requirements of the Vera Rubin Observatory. More propositions. So RNE network operators can design and build RNE networks in response to requirements or SLAs from major facilities. And RNE network operators collaborate and cooperate to design and build solutions that leverage their networks to support major facilities. So in conclusion, let us conclude with an answer to the question that we started with. So can major facilities leverage RNE networks to build effective solutions? And I conclude that the answer is yes. By collaborating and cooperating to design and build solutions for major facilities that leverage RNE networks, by leveraging the broader CI ecosystem on the campuses at the regional, national, and global levels, by leveraging the expertise, talent, and relationships in the RNE ecosystem in collaboration with the major facilities to build effective solutions. Thank you.
Great. Thank you very much, Julio. It's a great presentation.